Good afternoon, everybody. Hope you are all healthy and safe at home. We shall continue with our chapter 2, Hilbert spaces. So, in the previous lecture, we had seen the concept of Gram-Schmidt's orthogonalization process, and we had seen few properties related to that. In this lecture, what we are going to do is we are going to study about what is meant by separable spaces and some corollary related to that. So what is a separable space? A normed space X is said to be separable if there exists a dense countable set in X. So if the space has a dense countable set, then we can say that the space is separable. Okay, so this is a simple definition. You might have learned in topology and all also similar definitions we have done. So next we'll move on to the corollary 2.1.8. The Hilbert space H is separable if and only if there exists a complete orthonormal system set EI in it. Okay. For a normed space to be separable, it should contain a countable dense subset. That was a definition of a separable space. But there is a condition for any Hilbert space to be separable. The Hilbert space is said to be separable if it contains a complete orthonormal system in it. Okay, so let's see how we can prove this corollary. First of all, what we'll do is we will consider the Hilbert space H, and then we will choose let it is an if and only if condition, right? So first of all, let H be separable. Okay, H is a Hilbert space. Let us suppose that it is separable. So by definition, if it is separable, we can say that H has a countable dense subset, right? Has a countable dense subset, and I am calling this subset to be Y. Let Y be the countable dense subset of H. Okay, so this implies Y is equal to set Yi, where I greater than equal to 1, or I varies from 1 to infinity, be a subset of H which is dense. We will form a linearly independent set Xi of Y such that span of Xi, where I is from 1 to n, is same as the span of Yi, where I varies from 1 to nn, where this nn is some natural number, okay, which depends upon n. Nn depends upon the n. So from this, what can we say? I'm forming a considering a linearly independent set Xi such that span of Xi is same as span of Yi, where I varies from 1 to nn. So from this, I can say that if I is equal to n plus 1, okay, then xn plus 1 is equal to some yi where I will be greater than nn. Okay, by this definition, we can say that xn plus 1 will be some yi which is where I is greater than nn. So from this we can say that xn plus 1, it does not belong to the span of xi, right? It is not the linear combination of any of the elements because it is equal to some yi where yi is not in this span. I variation is I is greater than nn. So hence we can say that xn plus 1 is linearly independent from the set xi. right? We can say this. So we are having a linearly independent set with us, right? By defining in this manner, that is span xi is I varies from 1 to n, is span yi where I equal to 1 to nn, where nn is some natural number. We can say that this xn plus 1, any element apart from this set, will be linearly independent from the rest of the elements. So we'll have a linearly independent set with us. Now also by the definition of this set, we had said that span xi is equal to span yi. Now as the set yi where I is equal to 1 to infinity is dense in H, we can also say that the set xi, which is having the same span of set yi, is also dense in H, right? This is also dense in H. Now in the previous lecture we had learned about the Gram-Schmidt's orthogonalization process, right? What was the basic concept behind it? Basic concept was orthogonal, right? Gram-Schmidt's orthogonalization. So what we had was, if we are given any linearly independent set, we can form a orthonormal set from it. So by Gram-Schmidt's orthogonalization process, we obtain a system EI which is orthonormal, right? We get a orthonormal system, right? Now there was the property of the Gram-Schmidt's orthogonalization process that this system will have the same span of the linearly independent system that we are considering, right? This is the property of the sequence that is formed. So since span xi is dense in the set system, xi is dense in H, so span of xi will also be dense in H, and span of xi is same as span of ei. So this implies ei is also dense in H. Ei is dense in H. So what do we have? We have a orthonormal system which is dense in H. So if that system is dense in H, we can say that it is complete by definition of complete systems. So since we considered H to be a separable space, it had a dense subset, and with the help of that dense subset we formed another linearly independent set which is also dense in H. And by Gram-Schmidt's orthogonalization process, from this linearly independent system we formed a orthonormal system, and by the property we can say that this system set ei is also dense in H. So we got an orthonormal system which is dense in H. So we have obtained a orthonormal complete system. So one part is clear. Now we shall do the converse part. So for that, conversely we shall suppose that the space has a, say, set ei is an complete orthonormal system. Okay, orthonormal system. Now by definition of completeness, what we can say? We can say that the set summation I equal to 1 to n ai or ai ei for every n belongs to natural numbers, and for every ai this set is dense in H, right? So we have got a dense set in H. Now to show that if we are supposing that the system is complete orthonormal, we need to show that the space, Hilbert space, is separable. So by definition, for a separable Hilbert space, it should have a dense subset which is countable. So we have already got a dense set in H. We need to check whether this is countable. So how can we make this countable? I am just going to choose all these. This set is dense for every AI. So I am going to choose AI, choosing AIs to be rationals. We know that the set of rationals are countable, right? So choose AIs to be rationals. So we get a countable dense subset, right? Countable dense subset in H, and hence we can say that H is separable. So this is how we shall prove the corollary 2.1.8, that is the condition for the space, Hilbert space, to be separable. It is separable if and only if there exists a complete orthonormal system. So that was the proof of our corollary. So with this we shall wind up today's session. Thank you. Stay home and stay safe.